my objective tonight is to discuss thermodynamics as if you guys already knew about it, and if you don't, you have to say so, and I'll try to discuss it in the clearest, most obvious terms, but I will be jumping around conceptually. So when I do, raise your hand. So my contention in most of these lectures is that thermodynamics causes climate change, and that's really no different from the climate scientists. But climate scientists are using something called the first law of thermodynamics, which it relies on an energy balance. The energy coming into the earth has to balance the energy going out of the earth. My contention is that there's a second law of thermodynamics that's not being considered, and we need to consider it. What it says is that the condition of the earth or any system becomes constantly more disordered. Just what disorder means is another question we discussed last week. Becoming disordered means losing the distinction between different materials and energy types in the system. It becomes a very boring system without any differentials. So let's go on to that. This analysis is based on the second law of thermodynamics. The second law observes that every process, everything that happens in the universe creates disorder. To the early thermodynamicists, this meant that order was doomed to extinction. The ultimate fate of the universe was a totally disordered condition with no distinguishing patterns, uniform with no differentials of any kind, dead with no activity, a heat death, which is the term they coined to express it. There was really nothing happening here. Modern non-equilibrium thermodynamicists see it differently. To remain ordered, a system must have the means to discharge the disorder that it generates. Systems may become disordered depending upon their ability to discharge. Systems may become ordered or disordered depending on their ability to discharge disorder faster than they create it. Our world is a complex ordered system that discharges more disorder than it can accumulate, thereby becoming more elaborately ordered all the time. And we'll be able to explain some of that and why it happens. Some of the questions we'll be addressing is what kind of a system is the Earth? In thermodynamics, there are three types of systems. There's an isolated system that the boundaries of which can pass energy or matter. There's a closed system that can pass energy but not matter. And there's an open system that can pass energy and matter. And we'll be discussing some of that. What makes the Earth sustainable? Well, part of what makes the Earth sustainable is that if it runs out of order, it's not sustainable. But if it can just keep dispersing its disorder into the outer universe, it can remain ordered and be sustainable as it is. And an interesting sidelight is the Hubble telescope was devised by a guy who discovered that the universe was expanding. Well, if disorder is discharged into an expanding universe, it can just keep on going forever as long as the universe is expanding enough to keep holding it. And I think this is going to be an important area to study in the future. What causes the Earth to function? Well, function is to change in predictable ways. When something's not predictable, we tend to call it random, and we don't know what's going to happen next. But when something is ordered, it functions. Some examples of the Earth functioning are climate systems. As we'll discuss, climate systems are major circulations of the atmosphere. But I hesitate to call it global. I think if we talk about global warming and we make that equivalent to climate change, we've already got it wrong. Because global warming really is global. Climate change is regional. There are climate zones, and they have different climates. Does equilibrium cause dysfunction? Well, we have to explain what equilibrium is, but equilibrium is the complete absence of order. And since order makes things function, then equilibrium is complete dysfunction. And such a thing is not sustainable. And those questions go on, but I think you'll recognize them as we come to them. So what kind of a system is the Earth? The Earth is by definition a closed system. Energy from the sun passes through it. Matter doesn't. Why doesn't matter? Well, because the Earth has gravity and it holds all the matter it's got down. And because it's got gravity, it's kind of cleared the area around it of any matter that's there. So there's no transfer of matter into and out of the Earth. Those two things define what a thermodynamically closed system is. So now, what causes the Earth to function? Functioning and activity are related to order, and the Earth is an ordered system. Ordered systems function in proportion to their order, among other things, I have to say. The amount of disorder coming into the Earth as solar energy, I think I can point out. Oh, I've got to activate my pointer here. I can point out that there's 40 milliwatts per square meter of and there's a missing unit there per degree Kelvin coming into the Earth in solar energy, and there's 940 watts per square meter per degree Kelvin leaving the Earth. That's a huge differential. There's 20 times more entropy, more disorder leaving the Earth than is coming in. So you have a tremendous disorder differential, and that's inclined to make the Earth become an ordered system. How does it become ordered? Well, there are ordered flow patterns, and there are ordered material systems on the surface. But anything fluid is induced to flow, and flowing is a certain kind of order. we all know about ocean currents. These are there specifically because there's more entropy discharged from the Earth than comes in. In the atmosphere, which is also a fluid matter, the warm Earth warms the atmosphere on the bottom by convection, and it rises and cools and circulates back down, and we get these convection patterns that are common in weather events. And there are similar patterns that occur around the world, but not globally, but regionally. The tropics has a climate that's typical for equatorial regions, and the temperate climates are typical of temperate regions, and the polar climates are also typical of polar regions. But these are not global attributes. These are regional attributes. Order also occurs in matter. When you add a volatile liquid to the convection cell concept, when the volatile liquid gets up into the atmosphere and gets cold, it precipitates. It releases its entropy at an upper level and forms a liquid which precipitates as rain. If it needs to release even more entropy, it undergoes another phase change and becomes solid, and you get snow and sleet and ice like we're going to have tomorrow night. But biomass is not so much a physical transformation, but more of a chemical one. You take carbon dioxide and water vapor, which are both very high entropy materials, and you add sunlight, and you get sugar formation, which is a very low entropy material. Now, because entropy is always increasing, to get that low entropy material, you have had to have created a great deal of entropy. And the fact is that the entropy is released into that expanding universe, and the order is left behind. And I think I can show you that pretty clearly. So what makes ordered things dysfunctional? And what makes ordered things dysfunctional is when the entropy discharge is restricted in some way. When the Earth is able to discharge entropy, it can remain a low entropy body. But when something gets in the way, something like carbon dioxide, which by the way, restricts entropy discharge just like it restricts heat. Entropy and heat are very closely related, as we discussed last night. So when the discharge of disorder is restricted like that, the disorder tends to build up on the Earth because the Earth can't discharge it. What else can cause dysfunction of the Earth? How can the Earth lose its order other than retaining disorder? Well, it can lose its order by a a an occupant that is so anxious to create his own comfort out of the order of the earth, that he attacks the order of the earth and damages the system and destroys it. In what I've tried to show here is the existing order built up over the millennia can be stripped away. Harvesting the forests. We've destroyed the biomass on the earth by about 35%. So that this is another way that the order of the earth has been destroyed. Now is this really something that we need to focus on? I studied that for a little while, and I came up with this curve. This is a curve generated from data developed by a guy named Vaclav Smil. He's an energeticist at the University of Manitoba, and what it shows is that 20,000 years ago, the amount of biomass on the Earth was about 500 gigatons, and it grew to something of the order of 1,000 gigatons, and then it leveled off, and it decreased to something around 900 gigatons, and then it plummeted to where it is now. It's about 610 gigatons. And so looking at this data, I was stimulated to ask a bunch of questions, and I'll discuss what I found. 20,000 years ago is in the middle of the Wisconsin glaciation, and ice sheets had pushed all the biomass off of vast regions of the Earth. So there wasn't a lot of biomass on the Earth. But ice ages end, and the biomass began to take over again, and it regrew to about 1,000 gigatons. At that point, mankind began to discover agriculture, and he began to develop weapons and tools that used wood as a material. So he began to attack the order in his surroundings and use it to his own purposes, and to just clear it away, to make way for his agricultural activities. And that actually brought the order of the world down to this point. And what happened here is the development of the steam engine. This developed a new use for biomass as a fuel for keeping a steam engine running that was going to be doing your work for you. And that turned out to be such an excessive use that it exceeded the ability of the Earth to produce more biomass, and the biomass has been plummeting ever since down to this level. And it's just interesting to see these stages in the development of biomass on the Earth. And by the way, there is nothing saying what's going to happen to the biomass in the future. If it should follow this dotted line and come back up, and maybe there are things we can do that'll make that happen. That would kind of save us at the last minute. But otherwise, it tends to be plummeting straight down. And in another 100 or 200 years, we just won't have any. Like Easter Island and places like that, where the biomass has been destroyed by people who each individual has had the feeling that he could improve his existence by destroying what was there. So then I just wanted to have a few comments about sustainability. The first law says that matter and energy can neither be created nor destroyed. So if you're using up either one, it's simply being put into an unusable form. You aren't destroying it. And the second law goes along with that, and it says that a process becomes unsustainable because it accumulates too much disorder, too much waste material to continue its operation. It essentially runs out of order. We discussed how order makes matter functional. If we take the order out of matter, it becomes not functional anymore. And so I discovered this little sign on a vending machine, and we all interpret that to mean that it doesn't work. But the sign says out of order. That's exactly what the thermodynamicists have been telling us. When you remove too much order, the system becomes dysfunctional. And so what's happened here is there may be just a minor dysfunction. Maybe you can go to the hardware store and get a new part and fix the machine, but that's just replacing the missing order. So it's important that we recognize that if we allow the disorder of a system to build, it becomes dysfunctional. At some point, it's not necessarily out of order, but it's missing some very specific functional order. Order is incredibly important. Maintaining order is existential. We can't exist without it. If an individual organism can't discharge enough disorder, it becomes dysfunctional and dies. If a species cannot discharge enough disorder, it becomes dysfunctional and goes extinct. If an ecosystem cannot discharge enough disorder, it collapses. And if a planet cannot discharge enough disorder, it cannot support life. So living on a living planet, it's nice to know that we can discharge enough disorder to keep the order level on our planet high enough so that we can remain functional and stay alive. We discussed some of that last week. I had a little picture that showed an animal consuming ordered food and disordering it as waste and maintaining its own order. Life emerges, evolves, and thrives under the right conditions if the planet can discharge enough disorder. That's very fundamental. Biomass is one of the most ordered forms of matter. If the discharge of disorder from the photosynthetic process can't escape, the cellulose molecule can never be assembled. What happens is here is biomass creates this huge molecular structure, which is sugar molecules all interacted with each other into a massive fixed structure. That's really the ultimate in ordered atomic structure, and it does that by a process that continuously produces disorder. But the disorder escapes, and the order doesn't, and we'll discuss why that happens. There can be step changes in disorder. Order doesn't always. Order is not a linear function of temperature, but phase changes represent a large change in order or disorder without the temperature changing very much. And an example, as in this glacier, ice is far more disordered than water. Melting ice takes a lot of disorder out of the atmosphere and making it colder, and it puts it into the ice, causing it to melt and become disordered. We discussed last week how the addition of energy made something disordered. When you take energy or entropy out of the atmosphere, it becomes colder, and you put it into the ice, and it becomes disordered. In the same by the same token, in a desert, water is far more ordered than steam or than water vapor. That the addition of more energy evaporates more water, takes a lot more disorder out of the atmosphere, making it cooler and more ordered, and puts it into the water, causing the water to evaporate and become more disordered. So you can't disorder a system without taking the disorder from somewhere. Disorder moves between systems, like I showed you with the first set of slides that had the glass of ice water. So now, how do we assess the amount of order in a system, and what kind of property is disorder? Well, in thermodynamics recommends two types of properties. There are intensive properties, and an example is temperature and pressure. And they are independent of the size of the system. If you double the size of your system, you don't do anything to the temperature. You just have twice as big a system at the same temperature. There's our light system. There we go. And there are extensive properties, which are very, very dependent on the volume. If you like mass, and I've used volume as a property, but like mass, if you make your system bigger, you're likely to include more mass. Now order and disorder are extensive properties. A bigger system that includes more material contains more order than a smaller system. Ecosystems are an expression of order. You'll notice in the photograph on the left that I've labeled a mature ecosystem. You have a three-dimensional system there. And each leaf represents represents an amount of order. And so all the leaves that you see there, multiply that order 100 times. Multiply that order anyway. On the right, all that order has been removed. So the immature ecosystem, or the ecosystem that I've labeled immature, has less order or more disorder. You've destroyed the order in that ecosystem, even though it may look nice, even if it may be desirable for us. To destroy the order makes the Earth dysfunctional, and we'll get into that more as we proceed. In a leaf, for instance, there's a whole host of order all the way down to the molecular level, and that is reflected at more and more expansive levels all the way up to the world that we can perceive. All of this order is compounded as you expand your system size. Soil contains a lot of order, but that order can be destroyed as well. In the picture on the left, there are biological creatures that represent soil carbon, and these creatures are extremely ordered chemical species. In the photograph on the right, that all of those soil microbes have been plowed up, and they don't exist in that soil. So while that looks like an ordered system to us, all the order has been destroyed in that system. So that system becomes dysfunctional. So through evolution, nature has been increasing the order of the Earth for millions of years. If we want to live sustainably, we must do all we can to maintain and expand that order. Building upon what nature provides, we must encourage the processes that generate order and create the conditions that make it easy to discharge disorder from our planet. One of the things we have to do is accelerate photosynthesis. Photosynthesis discharges a lot of disorder, and it as we've seen, it results in huge amounts of ordered matter accumulating. We have to decrease greenhouse gases, which block the discharge of order from our Earth. We have to restore ecosystems, which is in some ways the same as accelerating photosynthesis. We have to restore soil carbon. We have to proliferate soil food webs and increase biomass in every form, and restore high hydrology. And this relates to accelerating photosynthesis. Maybe we'll get to that here. Maybe it'll be next week. And we have to balance and stabilize the climate. And I think we have a bit more to say on that. I want to discuss climate change and what it is and what it might be. The first law of thermodynamics discusses energy balances. And the second law discusses entropy balances. So now, climate change is currently being presented as an energy balance. So here we have a balance. We have energy coming in and energy going out. Okay, energy from the sun impacts the Earth and flows across the surface. It warms the Earth. And as the Earth warms, it begins to radiate energy back out. And as it becomes warmer and warmer, it radiates more and more energy until the energy radiating out is equal to the energy coming in. And at that point, the temperature of the Earth stabilizes. So you don't get very much temperature change when you have a balanced energy cycle. Now, incoming energy is not entirely constant, although it's called constant by climate scientists. They call it the solar constant. It's the amount of energy that impinges on the Earth. But it's really variable. Everyone knows this. The solar constant is variable due to things like sunspots and planet orbits and Milankovitch cycles. Milankovitch was I think it was Russian scientist that studied all of the things that affected solar input and found that it was a bit cyclical. So Milankovitch cycles tend to affect the temperature of the Earth. As incoming energy increases, the temperature at the surface of the Earth increases until incoming and outgoing flows balance again. So you have the Earth with variable temperature cycles. Likewise, if the outgoing energy flow is impeded, the temperature at the surface of the Earth goes up again because you can't get rid of this energy. Again, until incoming and outgoing flows balance again. Variations in incoming and outgoing energy flows cause global warming or cooling, climate change. That's the standard line of scientists at this point. And if that's all it were, that would be true, and that would be an adequate explanation. But it's not really true. In this case, climate change is considered an energy balance phenomenon, and that allows two systems, an energy source and an energy sink. And outer space. When energy flows across the Earth, it flows through one system that responds to the amount of energy that's flowing through it. But that isn't the case for the Earth. The Earth has to satisfy the second law as well, and so it becomes complex. It establishes multiple independent parallel flow paths for the energy to follow. The energy balance explanation would be correct if there were only one system carrying energy across the surface of the Earth. But the Earth has many different systems capable of carrying energy. The atmosphere, the hydrosphere, the biosphere, et cetera, et cetera. Solar energy travels through every available system, finding the combination of systems that offers the least resistance. When the resistance of one system changes, the proportion of energy carried by that system changes, and the proportion of energy carried by all other systems changes as well. So if what we really have is this, solar energy impinges on the Earth and distributes itself among several different systems. Now what happens is, suppose the biosphere changes. So it can't handle as much energy anymore. Now we still have the same amount of energy, but it has fewer systems to flow through. So it has to cram itself through fewer systems. So the atmosphere has to carry the energy that the biosphere can't anymore. So atmospheric weather becomes more violent. The hydrosphere, my favorite phrase is we've paved paradise and put in a parking lot. So the hydrosphere is now all out of whack. So the energy that it was carrying gets put on the atmosphere too. So now we have an explanation for why our weather becomes more intense when we destroy the other systems. We're just transferring that constant energy load. Now each pathway is a natural machine. A machine can create ordered energy, which in the case of the early scientists was considered work. Their interest was the amount of work you could get a machine to do for you. But order is not just work. Order is ordered energy in a number of different ways. For instance, in a rain droplet, you have energy coming into the rain droplet. You have radiant energy, white light, and because the edges of the droplet refract the wavelengths differently, when they leave, they're all separated and they become ordered, and you get all the red energy, all the red wavelengths together, the yellow and the greens and the blues, and you get a rainbow. It's an extremely simple system, but when you pass energy through it, it becomes ordered. It creates order out of disorder. This is really quite fundamental. In the atmosphere, we already went into convection cells, and how when the ground warms, the air rises and circulates around in a cell. This is now the energy coming into this system creates ordered flow patterns. That's now order. If you add water to this convection cell system, you have a system where there are phase changes taking place, and when the warm water vapor reaches a high enough altitude where it cools off, it begins to precipitate, and it releases all the entropy that was contained in the liquid phase into the atmosphere all the entropy that was in the vapor phase releases the entropy and becomes a vapor, becomes a liquid, and the liquid precipitates as rain. So this is a method to get entropy high into the atmosphere where it can be radiated away from the Earth. In the case of the biosphere, you take two high entropy materials, carbon dioxide and water, and you combine them with solar energy, and you get biomass, which is a big molecule that fixes a whole bunch of smaller atoms together in fixed relationships to each other. That's a very low entropy configuration. Now the amount of order in each system determines how rapidly that system can produce entropy. If you take the biosphere, for instance, and you destroy half of its order, it can't produce entropy as fast as it could before. If you take the hydrosphere and you interrupt its functioning, it can't produce entropy as fast as it could before. And the atmosphere, because the amount of solar energy coming into the Earth doesn't change, the atmosphere has to handle the whole job. And so the increase of disorder or the destruction of order requires that the atmosphere become more violent. Now, if I could just see my machine here. I guess I hit the wrong button there. There we go. Now entropy is the name for disorder, and it's mathematically quantified by this equation S equals Q over T. S is entropy, Q is energy, T is temperature. This is an interesting equation because it means that entropy and energy are not the same thing. That when the temperature is high, the same amount of energy doesn't have a lot of entropy. When the temperature is low, this amount of energy has a lot more entropy. So a high entropy content indicates a disordered system. Disordered systems are random, chaotic, and uniform. They cannot function. A low entropy content indicates an ordered system. Ordered systems are diverse, structured, and variable. They actively function. And my contention is that's what's happening to our ecosystems. That they are losing diversity. They are becoming chaotic. They're becoming uniform because they're losing species, and so they cannot function anymore because they are gaining entropy. Things to think about disorder. When entropy is removed from a system, the system becomes ordered. That is, you take disorder out of the system, then what's left behind is ordered, like the glass of ice water. If you take the water, the disordered fraction, out of the glass, you're left with just ice, which is the ordered fraction. So when you take entropy out of the system, it becomes ordered. When you add entropy to the system, it becomes disordered. Now, a system, depending on its constraints, one of which is temperature, has a maximum amount of disorder that can't be exceeded. And a system that's already at its maximum disorder, won't accept any more order. Won't accept any more order. One of the ways it will accept more disorder is by heating up. But a system must, to some small extent, be ordered in order to become more disordered, or in order to accept more disorder. The more ordered a system is, the faster it can assimilate disorder without heating up. So elaborate order is a buffer against heating up. So we have to make this planet ordered in order to prevent heating up. A reservoir of elaborate order is necessary to prevent the Earth system from heating up as it receives solar energy. Neither reduced fossil carbon use nor increased carbon sequestration can rebuild the order and complexity in the carbon mass of the biosphere. Only restoring order to the Earth can do that. So we have to set the system up so that we can generate order as rapidly as it was generating it 10,000 years ago. What happens when energy passes through a closed system? Energy comes from a hot source, high temperature, and flows toward a low source, a low sink. And in doing so, it flows through the system. When the system becomes steady state, the energy flowing in is equal to the energy flowing out, and the temperature remains constant. But in that case, the entropy flowing in is Q over T1, and the entropy flowing out is Q over T0. And so the entropy flowing out is much greater than the entropy flowing in. So we're extracting from the system more order than was flowing in the first place. So that closed system, that thermodynamically closed system, generates order. And it generates it in the material phase. That is, matter can't get out of that system because that's the definition of a closed system. Energy can flow through, matter can't. When the matter in the system becomes ordered, it can't flow out of the system. So the whole system tends to build up order. So as long as energy passes through the system, it takes out more disorder than it brings in. And such systems become ordered and or active. Since energy flows down a temperature gradient from hot to cold, any closed system in thermal balance discharges more entropy than it takes in. This results in a tendency for all such systems to become ordered. Now that is hard sell, because that's the opposite of what Carnot told us. He told us that systems all became disordered. But here's a system, and not an uncommon one, that becomes ordered. And it's because of the entropy balance. Every system has entropy flowing into it and entropy flowing out of it. And the activity in the system is generating entropy within it. And the entropy leaving is equal to the entropy entering plus the entropy generated inside. if the system is to be completely balanced. That's what this equation means. So if more entropy is leaving than is being generated plus what is entering, the entropy content of the system is being depleted. And so the system is becoming more ordered. If less entropy is leaving than is being generated, plus what is entering, the entropy content of the system is being increased. And so the system is becoming more disordered. It's almost that simple, maybe not quite. Okay, how does this affect the Earth? Well, the whole topic of climate change is about climate, and climate is a regional phenomenon, not a global one. And the tropical climates are those where the most energy enters the system because the solar energy impinges on the equator, and they become the warmest. And because they're the warmest, they radiate the most energy back out into space. Now, when you radiate energy back out into space, you're extracting entropy from the system. And when you do that, you leave the most order. And what do we have around the equator of the Earth? We have an immense rainforest. And our concern is that the rainforest is being burned all through Brazil and all through the equatorial Africa. And this is quite consistent, that extraction of the entropy leads to order. And we have three different climate zones. When we extract entropy, the factors that differentiate those climate zones blur. And you tend to get one climate zone instead of three. So it's shown the droughts in California, for instance, are due to an expansion of this equatorial climate zone by expanding its boundary northward. And when that happens, ecosystems on the north edge of this begin to dry out and turn to desert and become hotter. So that climate change in California is directly related to the entropy exchange along the borderline of the tropical zone and the temporal zone. An interesting observation that I'm kind of working in the back of my head is this northern climate zone also expands northward as the Earth warms. Well, the area on the equator where there's a lot of energy absorbed and the air is rising carries water vapor with it, and when it condenses above, it creates rain, and so you get high rainfall area there. When that's reversed, that this dry air from above is dropping down onto the Earth, this is a band of relatively desert area. The Sahara Desert and the Gobi Desert and the various deserts are generally on that line, and that's what's happening in California. It's drying out. It's becoming a desert, but it's covered with biomass, so it's burning at this point regularly. Now suppose we, at the present moment, this cycle flows this way, and the air, the dry air from above, is projected down onto the surface of the Earth, which makes this polar area a polar desert. It's very dry. There's snow up there, but it's there because it's been there for 100 years and it doesn't melt. But there's not very much precipitation there. But if this interface were to proceed northward enough so that it included the pole, then this area of rising air would be at the pole. Well, this is the area where a lot of precipitation occurs. Now when that happens, if it's at the North Pole, then this precipitation will be happening as snow and ice and frozen solid form. That creates glaciers. When a glacier occurs, that pushes all the biomass back. And so glacial cycles may be caused by just exactly that phenomenon, the increasing of the what am I saying? The increasing of the climate zones to the point where the Earth can only hold 2 of them instead of 3 of them. That would very, very cleverly explain why we get glacial cycles. Now we've already been through this. There are several different ways that the Earth can create order through energy flow. When biomass is destroyed by these various mechanisms, it can be destroyed by low entropy processes. An example of a low entropy process is conversion of water into ice. When this happens and an ice age occurs, biomass is obliterated by low entropy ice. Now that forces glaciers to grow, and that pushes the biomass off the planet. Well, we've just seen how when the biomass diminishes, the climate tends to warm. When the climate warms, the glaciers tend to retreat again, and so this climate system cycles back and forth. That's a good thing. That's a low entropy system. But if we have a high entropy system, the moisture tends toward the vapor phase, and when that happens, it's not available in the liquid phase to grow plants with. So rather than glaciers growing, deserts expand. So biomass can't stand the heat; it gets out of the kitchen, and biomass diminishes, and that only makes the climate warm some more, and the deserts expand some more. So this high entropy kind of a system leads to continuous and accelerating warming. Now, in the particular instance that we're looking at, when mankind is the destroying angel, mankind obliterates the order content of the biomass. The biomass is reduced. It can't perform its objective. The climate warms. deserts expand, and the whole cycle occurs all over again to a continuous and accelerating warming situation. So either of these situations leads to continuous warming. This situation leads to cycles. And we've gotten as far as we have because we have always been in this cycle. But we don't want to let that entropy grow, or we'll be in one of these two cycles. In the case of global warming, I want to assert that climate change and global warming are really not the same thing. In the case of global warming, the energy flow from the sun increases, or the energy escaping from the earth decreases. Either way, the earth actually warms up. The whole earth warms up all at once. So that is actually a global warming process. But that's not what we're observing. We're observing poles that are warming much faster than the equator. And this is...
So would you call that a first law description? Yes,
exactly. Yes, that's what I would... How did you guess? Yes, that's what I would say. Now, in the second mechanism that I call global equilibration, we are diminishing two out of three systems and dumping the whole load on the one system. Now, you don't have to have increased energy coming from the sun to do that. In fact, that won't do it. It's the destruction of this complexity that is making this happen. And when that happens, the Earth's temperature becomes more uniform if the mechanisms of heat transfer distribute the heat more evenly across its surface, so that areas that are usually cold warm up. Areas that are usually hot tend not to warm up so much, or maybe they even cool off. I'm not sure anyone has measured that the equator is cooling off, but the atmospheric heat transfer machine transfers heat more evenly than the other two machines, as it takes on more energy transfer duties. Disabling the biosphere and hydrosphere heat transfer mechanisms diverts all energy transfer to the atmospheric system, pushing the Earth's surface toward equilibrium and uniformity. Well, equilibrium and uniformity are the two no-no terms. They're the two dirty words. When the Earth becomes uniform, no complexity can be left. And this is how the polar and the temperate zones can all appear to be warming up, and the equatorial zone cannot appear to be warming up so much. And this mechanism doesn't require any change in solar heat input. It just requires a change in the complexity of the surface of the Earth. And by removing the forests and by damaging the ecosphere, we are in fact changing the complexity of the surface of the Earth. We're damaging the complexity of the surface of the Earth. So now, if we take this low entropy system and we remove all the activity that's going on, we get basically this system. The temperature in that system has been calculated. It's called the equilibrium temperature, and I have a whole lecture on that. It's not an equilibrium temperature, but it's called the equilibrium temperature of the Earth, and that's 59 degrees. So when the whole Earth turns to 59 degrees, all the ice at the poles melt, and the equatorial temperatures don't change an awful lot, but they change some. They might even cool a little bit, and I'm not sure anybody's actually studied that out. So Mother Earth produces more biomass and more glaciers to become more ordered. We need to help her out by creating conditions that enable her to do more of the same. These conditions can be created by large-scale afforestation projects, ecosystem restoration projects, and by soil carbon reclamation. And some examples of what's being done. Maybe some of you have heard me talk about the Loess Plateau over in China. The Loess Plateau, when the winds blow across the Gobi Desert, it picks up huge amounts of sand, and like snow going over, like wind going over a snow fence, it drops it on the other side of the next obstacle, which is the next which is a mountain range in between. And it drops all this sand onto this area called the Loess Plateau. Loess is just another word for wind-blown soil. So this loess soil is very prone to erosion, and it used to be a primeval natural area, but the farming in that area has destroyed the soil so much that it's all gullied, and it's been called one of the most eroded areas on Earth. Anyway, it's a huge area, as big as the country of France, and it's essentially turned into an eroded desert. Now, 15 years ago, probably more like 20 years ago now, China decided to do something about it. And they initiated a project that so far they've planted 70 billion trees, and in an area 2,800 miles long, and this amounts to 42% of China's forested territory. And in 15 years, the climate and the biology of the area has completely changed. From going from this kind of a aspect before the project to this kind of an aspect afterwards, and that's in 15 years. Going from this kind of an aspect before the project to this kind of a project now. Notice how much use they've made of terracing and riprap on the slopes, and they plant permanent stuff on the slopes so that they're not tilling that soil. They're keeping it where it is. And what they're finding is the level of groundwater in the aquifers is coming back. There's streams that were dry that are now flowing. So an awful lot has taken place in that particular project. Now, that's a desert, but it's not an equatorial desert. And that makes this a particularly good area for that project. You don't have quite the same blistering heat that you do, let's say, on the Sahara Desert. But this Great Green Wall of China, Great Green Wall of Africa project takes the lower Sahara Desert, called the Sahel, and it's designed a wall of trees to go all the way across this whole area, 4,700 and some odd miles long. And here's a picture. See the green line is where this forest will be created, and they are able to not grow a forest like we consider a forest, but this is an example. These are mostly acacia trees that are extremely drought resistant. But once they shade the ground, certain grasses and stuff can grow underneath. So these forests are being created on the Great Green Wall in Africa. And a newer project is the Sinai Peninsula project. They are making huge hydrological changes to areas in the Mediterranean Sea, where all the drainage from the peninsula creates a more fresh water area in lakes along the coast, and that tends to change the climate in the depression in the middle of the peninsula. So that this is brand new. This project hasn't been undertaken yet. But I'm very proud to say that I've been communicating with them and I've been asked to participate. So those are three examples of biological instances where thermodynamics have created a situation where the climate becomes ordered instead of disordered.
Are you familiar with Gaviotis?
With what?
Gaviotis? It's
Not really.
I believe it's in Bolivia, but another ecosystem restoration project on a regional scale.
Mm-hmm. And there are some in the Middle East. Israel has always been big on forestry, and they've been creating forests over there. It's just amazing. So now let me just make a few statements. Order is generated when entropy levels decrease. In other words, when you extract disorder. When the Earth discharges more entropy than it receives, its systems generate complex life. Then it receives and its systems generate complex life forms emerge. When the Earth discharges the same amount of entropy as it receives and its systems generate, it is sustainable, but it does not evolve. In other words, there is a 0 point where the Earth just has to discharge enough entropy to make up for what the Earth generates, and then there's really no change occurring. When the Earth cannot discharge as much entropy as it receives, its systems generate, as it receives and its systems generate, complex life forms go extinct because the Earth is not discharging that entropy. And entropy levels can only decrease, and a planet can only become more ordered and complex if its entropy discharge is greater than its entropy intake plus the generation of entropy. If entropy discharge can't keep up with entropy generation, entropy level increases. In other words, it becomes disordered. And we can't live in such a place. When entropy level increases, complex living systems fall apart. Complex life forms like the megafauna go extinct. So this concept that an entropy balance is responsible for evolution is a big deal that's been more or less overlooked by even climatologists who have been responsible for figuring out what's wrong with our climate. And the fact that, you know, when Charles Darwin first discovered evolution, he thought it was just a matter of living systems. But our climate becomes ordered or disordered by entropy discharge too. In other words, our climate evolves. And in fact, Earth systems, geology evolves, but geology is mostly solid matter. It's much more constrained than the rest. So it changes much more slowly. And at the bottom, I've noted some early physicists who began to discover some of these things as early as 1944. And this guy Ilya Prigogine, who did most of his work in the 1980s, he discovered that biomass is actually what he called a dissipative structure that dissipates dissipates entropy into the atmosphere. When we destroy the biomass, we're destroying the dissipative structure that's responsible for keeping the Earth ordered. And I think that's just fascinating. So that's pretty much where I was going for tonight. Can we have a discussion?
It's the same Schrodinger's cat thing.
What's that?
The same Schrodinger's.
Yes, it is the same one. Yes. Yes, he wrote a book, What is Life? And it was published right around 1944. And he discovered that life is a process that dissipates or discharges entropy faster than its metabolism creates it. So that it not only remains order, but its order tends to grow. And that's why life is so dominant on Earth, is because it's just been growing in that sense. Yeah, Schrodinger's cat. That's what he's famous for. So I'm gonna try. I wrote up a synopsis of last week's lesson, and I will try to write up another one this week. I get kind of lost as I do it because I've got other things pressing me, but I will circulate it to everybody.
Struggling with these concepts.
Me too.
So if we take the planet as a spheroid circling around the sun, and it evolves over time to develop an atmosphere.
Oh, yeah.
To develop the ordered
Yeah,
systems.
yeah,
that
actually.
allow life to.
As a matter of fact, I like that example because that's not necessarily pre-life, but that's certainly very early in the whole cycle of things. And so if the atmosphere evolved before there was any life, it's a good example of how evolution can go on without life. Anyway, obviously there was some life before that.
Oxygen is the most toxic substance on the planet.
Yeah,
If you're an anaerobe, right? So at some point in that evolution, photosynthesis started, and the atmosphere freed up oxygen, which shifted the dominant species on the planet from the anaerobes to the aerobes, or
Right.
at least dominant from our terrestrial perspective.
Right.
So conceptually, at that time, the Earth was discharging more entropy than it was
Right.
accepting.
Yep.
What were the mechanisms that were unique to this planet versus other planets? Was it temperature gradient?
Oh no!
Or-
Yes, I think it's the difference in the intake and discharge temperatures. That you know the entropy coming in from the sun is defined by that temperature of 5,700 degrees or whatever the temperature of the sun is, and the temperature, the energy discharge from the Earth, the entropy discharge is defined by that 288 degrees Fahrenheit, which is the approximate average temperature of the Earth, adjusted for the carbon dioxide in the atmosphere. And so that entropy balance allows enough entropy to discharge for the kinds of activities and the kinds of structural order to emerge and grow on the Earth, and you need just those circumstances for entropy to increase. Now, for entropy to increase doesn't just necessarily mean life. That determines the amount of order on the final planet, and that amount of final order may be very small. I mean, all these other planets, Venus and Mars, and even the big gaseous planets, Jupiter, and they're not completely disordered. There's some order there, but it hasn't reached the degree of self regeneration that makes it alive. It's just reached a certain order level that's still dead but not completely disordered.
Well, I mean, on some level, the discharge capacity, the dark side of the planet, is somewhat static, or right? The night sky is the night sky, and taking the variable of the atmosphere out, its ability to radiate or absorb radiation or whatever would be relatively consistent versus the sun, which is having sunspots and our proximity to it is more dynamic and more variable.
Yeah, I don't know how something like sunspots against a 5,700 degree background. I'm not sure how much of a difference exists. it's enough to make a spot visible. But it may be, is it 5,600 degrees or is it, 2,500 degrees? I don't know.
Okay, there's something there between the balance of what's coming in and what can be dispersed.
Mm-hmm.
And as you move farther from the sun, your dispersion would be greater. But you may not have enough base energy to fuel
But
living systems.
But in radiant energy doesn't change as it travels through space. And so even though the rays get further and further apart, so that it is dispersed, the amount of entropy per photon remains the same, no matter how far it goes.
Right, but photons per square meter on Earth.
Absolutely.
On Jupiter.
Yes, absolutely. Yep. Yep. Yeah, no doubt. It'll be interesting to find if there aren't levels of life that persist on other planets that are so primitive that we wouldn't really notice, but that are in fact self-regenerating and
Right. Or unrecognizable to our energy intensity.
right.
So I'm still struggling with this. Jump in here, jump guys. The concept of entropy as a substance is like, I think that's where
Yeah, but
First-
energy isn't a substance either.
right, but at least thinking at the photon level,
It's intuitively easier for you because you've always thought that way. But
I understand, the volume of a gallon of gasoline and what it can do, right? So I can conceptualize energy as a thing because I can in my mind's eye understand what it is, at least as it's captured in that chemistry.
Mhm.
Whereas entropy, I don't think in terms of photons bombarding the system and energizing or exciting and creating order or disorder by their presence, their accumulation, or their discharge, or their flow. I mean,
I just read a book that I don't particularly recommend because it's sort of disjointed. It's not very well written, but it's by a fellow who is professor emeritus at the University of Arkansas. And one of the things he says is that entropy is the driving force of the universe. Now that's incredible to me because, all my life I've heard that energy was the driving force of the universe, but the need for everything to become disordered is so great that it represents a driving force greater than that of energy. And I think that's fascinating. Yeah, I love Jeremy Rifkin. I've only read, I don't know whether I've read more than one of his books, but.
okay, well that's like 1980,
Yeah, probably.
1975, something. I mean, like it's as old as the early popular science descriptions of global warming.
He wrote a book called Entropy.
Entropy is actually.
Oh, is it really? Okay. That isn't the one that I've read.
No?
But no, but
Well, I mean, it had a more sociological perspective, but it essentially took the concepts from physics and tried to apply them to society. And you know, he's writing on the backside of you know, cultural revolution in the 60s and 70s. So he's trying to use the concept in physics to explain a lot of other things, but essentially that's what this conversation is doing as well.
yeah. And a lot of this is applicable to things like economics. You know, that if you can find the right analogies to say that, you know, this may be a return on a dollar is equal to is analogous to entropy, then you know you can put together a better, I think, kind of economic system than our present one. We just happen to keep our present one because it's too hard for us to make changes in our economic system. They're usually winners and losers, and the people who have successfully committed to our present system turn out to be the losers if we change the system. So. Mm-hmm. I agree. Yes, I think the fundamentals of thermodynamics are really much more widely applicable than they are used. You know, it takes some imagination to expand them into other fields, but when you do, it works. Well, like for instance, information technology. You know, the word entropy is used for, you know, the amount of information in an encoded message, and you know why that's an acceptable analogy. I'm not 100% sure, but I know that works, and I know that they use it all the time.
Well, I think because entropy is so closely associated with randomness, and encryption is really, you know, its strength is in its randomness. So I'm trying to go back to my professional work 20 years ago in designing ecological systems that were trying to break down wastes in water. Right? Yeah. So
well, that's right. I remember you mentioned it before, and I was so pleased that you were a John Todd
associate.
Associate of John Todd.
But you know, that concept just was if you have a waste, let's say you have water that is contaminated with acid, that is in many ways it is toxic to biota. But if you develop an ecosystem where that gasoline becomes food, then you can essentially clean the water of gas, right?
So
And
you have microbes that would thrive on petrochemicals.
Yeah.
And you figure out which ones those are and introduce them into that system.
right, and what, what we would do is, it's going to aquaculture, fish farming. The easiest way to start a fish farm is start with pond water, right? Because it's a living water as opposed to starting with sterilized tap water, which has none of what the fish needs for the ecology that it exists in. And these systems we built rely on fixed film bacteria. So microbes that wanted to hang on to something versus living in a slurry that was constantly swimming, activated sludge. So, and so the best way to fill a container with surface area that biology can live on is do it with plant roots, because it will invade the volume with the maximum possible surface area because it's doing it at the cellular level. And you have cellular respiration going on. The plant is delivering oxygen and other nutrients to the water. So plant roots become the surface area for a biota that can then start to disassemble the complex molecules that are aqueous in the solution. So we would build a system, plant it, and then go collect water from the mud puddles around gas stations. Right? Because where are you going to find the biota that eats gas, but around a gas station, right? That's a relatively simple one. With polyaromatic hydrocarbons and coal tars and all kinds of nasty hydrocarbons, as well as sewage and fat soils and grease from slaughterhouses and blood and proteins and all these different things. You could design ecosystems that allow biota to populate that could deal with that particular waste stream. And what systems are particularly good at is extremely volatile flows of waste in the stream. So a factory that produces ocean spray drinks one day, where it's getting sucrose and fructose and some other fruit material. The next day they're making mayonnaise, which is eggs and oils, and the next day they're making tomato sauce, which is acids and these ecosystems could handle surges of very different wastes once you've acclimated it to all those different wastes. So we would describe that system as utilizing entropy to dissect essentially, the waste coming in is energy in a very complex form, but it happens to be a pollutant in that form because it gets natural waters and it creates a rapid consumption of oxygen, which kills the aerobic life in that body of water. So we're trying to get those complex energies out of the water. And we would try and design a system that allowed for the maximum variability of pathways in order to do that. Right? So to use the terminology I've learned here.
I like that pathway analogy. I think that's particularly good. And you notice I used it in terms of complex systems. There are several pathways. I think part of treatment stability would be how many different pathways do you have?
Right, that you can simultaneously support to deal with whatever is going to come down the pipe tomorrow.
Yeah.
So plant material, the biota, that resides in the system, is resident in the system, in this context would be considered highly ordered and capable of dispersing entropy?
Yeah. Well, they're the result of a system that dispersed the entropy. Yeah.
So the system disperses entropy by taking complex molecules and reducing them down into their constituent
Well, you know,
components.
entropy and energy are so much alike. You know, all you have is Q over T, and if the temperature doesn't change, then entropy and energy are the same, because you know T is no longer a variable.
So if our system is metabolizing the energy
Yeah,
that is in those
so
complex molecules,
the release of energy is always the release of entropy as well.
okay, even though the release is in the form of carbon dioxide.
Yeah.
So the release of energy is the same as the release of entropy mathematically. Are they linear to one another? Would they
No,
occur on
they're
a
not.
curve that's based on temperature, or?
No, they're not. It's a big curve that goes like that, and it at very high temperature it comes together so that the amount of entropy is almost zero, and all the way down to zero, it approaches something like 1, and it's a big sweeping curve like that.
So as energy increases, entropy increases with it?
Yeah.
Do the curves ever cross?
Yes. Do the curves ever cross? I don't think so, but I don't know. You're a little bit beyond my thinking. But I don't know. I'll have to do. That's pretty fundamental work, mathematical work. I think it'd be fun to do, but I haven't gotten to it.
I have no idea what the units would be on either axis. I assume temperature.
I think that would not be hard to work out. You know, it's the I'm just not far enough advanced to make a concrete idea. S equals Q over T. If you, the amount of entropy that's taken out of the system is the integral of Q over T, and the integral of 1 over T is the natural log of T. So that you have a log function, and then my mind kind of boggles. But and I also get hung up because sometimes I mistake T temperature for T time, and that bothers me just mentally before I even pick up a pencil to do it on paper.
Well, but energy isn't a time function.
Well,
that becomes work.
it depends on. It depends on if it's. You're saying temperature isn't a time function.
Well, temperature isn't a time function either.
If you're extracting energy from a system, then the temperature is going to respond.
Right, but neither of them are particularly time dependent.
No.
They occur over time,
Yeah.
but I wouldn't think that the speed at which it happens governs the levels. Just governs the speed that it happens.
Well, especially if it's in a steady state system where there's energy coming in to make up for the energy that's being drawn out. Yeah.
Okay. Well, and if it's internally generating at a faster and faster rate, because it's not dissipating as fast.
And I wonder if something natural doesn't say that it must do that. You know, I don't have an answer to that. But that's pretty fascinating stuff. I mean, it's like a bank account grows faster and faster as it gets bigger and bigger. Maybe there's something equivalent to that in entropy that makes it become more ordered faster as it ages.
Well,
That would be interesting, wouldn't it?
biological populations
Yeah, they do.
are exponential
Mm-hmm.
growth.
Yep. Well,
So have you read What is Life?
I have seen it. I haven't read the whole.
I didn't find Schrodinger's cat to be particularly accessible writing.
I've never been very convinced by it, and I'm not sure whether that's because my mental level is not as high as his, or whether I'm really that much smarter than him and I can tell his ideas are no good. But yeah, I mean, it does seem rather trivial.